Hey, Isaac.
Hey Professor, I just read your email about
Yep.
the correlation for like laminar flow in like inside the cylinder.
Yep.
Um why can we assume that there's constant heat flux? Is it just because like there's going to be heat transfer between the two fluids?
Yeah, essentially. So, you kind of have to make an assumption there because, we've only done internal flow for either constant heat flux or constant surface temperature. Um, but in this case, since we have a counterflow heat exchanger, remember for counterflow, the two fluids kind of go in opposite directions. And so the difference in temperature between them is about the same all
Yeah.
throughout. And so you can kind of assume that there's a constant heat flux all throughout
Okay.
this.
Can we make the same assumption for like parallel flow in the heat exchanger? Because I know for the parallel flow, like you have like um a very high like heat flux, right? In the beginning, since
Mhm.
like the change in temperature is like very drastic, but then it kind of like levels off. So can we
Right.
make the same assumption?
So
Or
for the purpose of this class, you can, but in reality, the parallel flow heat exchanger doesn't really fit into either category because both the temperature and the heat flux is changing all throughout the heat exchanger, and so the parallel flow is a little bit of a complicated situation where you can't really it's hard to justify one's assumption or the other one. But for this class, like if that kind of question showed up on an exam or something, I would tell you which one to use.
okay, cool. Thank you.
Mhm.
Professor,
Yep. What's up?
can I ask you a question?
Sure.
For homework 6, when it's asking the hold on, sorry, let me just quickly bring it back up. For the written for like the the short answers
Yep.
for B I can correct me if I'm wrong. For the compare and contrast, like when we're doing the parallel and counterflow, would it be fair to say that the parallel flow will have the greatest heat exchange? Heat exchange, yeah, in the sense of that, like if you think if I was thinking about how like both the hot and the cold source kind of start at the same point, um, that will have like the greatest technically the greatest heat exchange, whereas the counterflow, um, when you get to when they both start at opposite ends, it will have a continuous heat exchange because of like you're there's always going to be a difference in temperature, but it won't have that much of it maybe it won't exchange as much heat from the hot source.
You're almost there, and so everything you said was right, but it's kind of more in the amount of distance that the heat exchanger travels, right? So for
Yeah.
parallel flow, absolutely. So at the very beginning of the parallel flow, you have the biggest temperature difference, and you have the biggest amount of heat transfer there. But then as the parallel flow heat exchanger goes along, then that temperature difference gets smaller and smaller, right? Because
Yeah.
the hot fluid will cool down, the cold fluid will heat up,
Yeah.
and so. Oh, go ahead.
Oh yeah, no, that's what I was thinking too, where like if you take it to extremes, the parallel flow there won't be any temperature difference. Whereas for the opposite flow, there's going to be at least one point where there's no temperature difference, but other than that, it will be there will always be a difference in temperature.
Right. Yes. Yes. So, what you and so kind of the question of which one, how do you compare the two? If you have just a very short amount of distance, so let's say that you're designing a device and you only have just a small amount of space to put a heat exchanger, you want to do parallel flow in that case because you have a very large temperature difference. You get a much higher amount of heat transfer in that short space. But if your goal is to exchange as much heat as possible between these two fluids and space isn't a concern, then you would use counterflow because in counterflow, you have much more space and you can have that much more consistent heat transfer over a longer space.
Okay, so it's kind of like first is like a long-term plan for or versus a short-term plan type of thing.
Exactly.
Almost.
Yep.
Okay.
Yeah, you can think of it like that.
Hi, Professor.
Hey, how's it going?
I am here for the arrow thing.
Yeah. Long time no see. How you been?
I know. Pretty good. How are you?
Good. Just hanging in there, ready for pandemic to be over.
Yeah, I bet. So you moved to like a whiteboard type thing? Because I know for a little while you were doing it like on a physical whiteboard, right?
Yeah. So I have my iPad right here. So I join kind of
Yeah.
with my iPad and then I just write on this thing. So it's not perfect because this stylus is already kind of beat up really bad, even though I bought it just a year ago, but it works okay.
Yeah. Yeah, it's been interesting.
How are you? So are you graduated already? I thought you graduated last year.
No, I'm graduating this year.
Okay.
Yeah. That's why we're trying to get some people in for the next generation of all the legacy teams.
Gotcha.
Yeah.
Was it just so you got free beer? I'm sure you get a lot of people.
I don't know if how the school would feel about that. I think you're right that it would get a lot of people. I don't know how the school would feel.
Oh, that's one way to use up your budget if you need to.
There you go.
Personally, I don't care. So take that as you will. But maybe someone else in the school might care.
Yeah.
Yeah. Because I'm in I'm trying to join the formula team, and Jake was talking about like how we're gonna, because they're trying to figure out how to use up the money that they have for this semester, because like I think they say they can't really quite build the car because they don't have access, but they're hoping like maybe get the materials and stuff for the next team for the next years or for the next team. And we're all jokingly saying that we should spend it on solid gold parts.
Yeah, we're kind of doing like some of the same stuff. We're actually trying to build it this year, so we're not sure how much of the budget we're going to need. But if we do have some extra, we're going to just try and get whatever we can to help out the next year's team.
Yeah.
I think Formula is going to end up. I think their goal is to have a rolling chassis by the end of this semester.
Yeah, because like another one they were talking about how like we like for next year we can start over, but at the same time like or at least for like the chassis, but or we can keep it similar. Was that this? No, I don't think it was chassis. I think it was suspension because like I remember him. I think it was suspension because he was telling me how one of the team members they did over 400 calculations, or they did 400 simulation runs on the suspension or something like that, I guess.
Oh, I'm not sure.
Yeah.
Yeah, Formula is a lot of work.
All right, Tyler. So I enabled screen share, so you can go ahead and
Okay,
share your
sweet.
screen. Yeah.
Let me do that. You want me to start now, or you want to wait until 2:30?
We can wait till 2:30. Usually people kind of mosey in like first 2 or 3 minutes in class.
Shared the wrong one.
Yeah.
This one. There we go. You guys can see my screen, right?
Yep.
Cool.
Mm-hmm.
It's the one benefit to COVID. I would have probably been nervous about doing this if it was in person, but on Zoom, there's nothing really to be nervous about because I'm just sitting at my desk like usual, You
have a good that's a good perspective about it. Usually people I've seen that it's sometimes harder for people to speak on Zoom just because it's hard to see how people are reacting to
Very impersonal almost, unless you have like everyone has their camera on.
Yeah.
Yeah, one day I am happy though. I took the speech class or whatnot. The professor practically had us like every other week do like 1 or 2 speeches on a subject or something.
Sounds terrifying.
Yeah, surprisingly, the time went away fast. Like we were
Yeah.
all nervous because like we had like I think like a 10-minute or a 15-minute speech, and everyone we were all nervous. But just like when we actually started to speak, though, it was like at least for me, it kind of went fast because I was able to have talking points and whatnot.
You guys see the Titan Arrow presentation slide, right?
Yep. Mm-hmm.
Okay, because
Yes,
it's
sir.
I don't know why the screen sharing options are on the other monitor, so I wanted to make sure it was sharing the right thing.
Mm-hmm. All right, it's 2:30, so let's go ahead and get started today. Good afternoon, everyone. So today we have a special guest. So we have Tyler Mudge here from Titan Arrow, and he's going to spend the first 5 minutes telling you about what Titan Arrow is all about and to maybe convince you guys to join it for next year. So go ahead, Tyler.
Thanks, Professor. Hi, everyone. I'm Tyler. Good afternoon. Okay, so Titan Arrow is one of the legacy teams for Cal State Fullerton. It's been a legacy team since 2014. And it is associated with the American Institute for Aeronautics and Astronautics. It's recognized in 85 countries because it participates in an international competition. And it's mostly STEM majors, but it's open to anyone who is interested in aerospace. All right, so in the design process, you can expect to do both 2D and 3D design. manufacturing, which will be a lot better to do once COVID is over, a lot of system integration, testing, and then the Society of Automotive Engineer Aerospace competition, and a lot of team collaboration. And then the way this year's team kind of broke it down, we had 3 sub-teams. So in the blue is what the airframe team was responsible for, green is the dynamics team, and then red is the CDAs, which is colonist delivery aircraft. So we have to follow the guidelines for SAE's competition rules. So it's got an 11-foot max wingspan. It has to be limited to 750 watts for the propulsion. It's got to be able to get up to 100 feet in the air and release both static and dynamic cargo onto a drop zone and maintain steady level flight. And this is just a picture that we pulled from one of the previous year's competition. I think this is Georgia Tech that had this one. So this is our current model. So we designed all of this last semester, and this semester we're currently building it. We call it our PA, primary aircraft. This is where we are currently in the manufacturing process. We have been doing it out of garages and out of one of our team leads' dad's engineering shops. So we've been trying to adapt to COVID, and this is where we are thus far. If you can see here, it's foam core wings that we do fiberglass and epoxy resin on them to make them strong. That's the lightweight design we went with this year. So this is our payload design. The Nerf footballs represent habitats because the whole simulation of the competition is supposedly colonizing Mars. So these Nerf footballs are habitats, and then these contain water bottles. And of course, the water bottles have to not break upon impact with the ground. These are our colonist delivery aircrafts. This was actually my sub-team. So we had to design these, which are autonomously guided gliders that will be released from the primary aircraft. The ping pong balls are colonists, as you can see with our little astronaut here. And we have to design the fuselage and everything, and then all of the control surfaces. And we use commercial off-the-shelf guidance systems. It's a Pixhawk. And the main challenge for us was that our maximum weight was 9 ounces. And that is not a lot of weight to try and build a glider out of. So some of the benefits of being part of the team is that it's really good on your resume. For an example, last year's team lead works for Raytheon now. Someone on the dynamic sub team has a job lined up for them at Raytheon again when they graduate. And I actually recently interviewed with Raytheon. So I don't know, well, actually I do know why, but Raytheon really likes this, this team, probably because it has to do a lot with a lot of what they deal with as well. But yeah, it's really good for your resume, and it can help you get a job in a top engineering company. So I'm going to put a lot of this contact info in the Slack chat, so you guys don't have to worry about writing this all down. But yeah, these are some important contact info, and then I'll put this information in the chat. Yeah, that's it.
Great. Tyler, if you want to send me this information too, then I can send it out as an announcement to the class, and then it'll be on the Canvas site, and anyone can reference that too. Okay.
Yeah, sweet. I'll email you the slides.
Great. And I'll send that out.
Okay. Thanks, Professor. Thanks everyone for listening.
Yep. All right. Thanks, Tyler. All right. So now we'll go back to our regularly scheduled programming. Just go ahead and share my screen back again. All right. So how's everyone feeling today?
Good, sorta.
Midterm this week.
Yeah.
That's one way to describe it. Yeah.
Probably should have not went work on Thursday, because I kind of pushed back on some of my other stuff.
I see. Well, I mean, hang in there, everyone. We're on week 13 already, so this is the time when I think things start to really get tiring, and I can kind of feel that too for myself. This past weekend I caught up. I try to catch up on as much sleep as I can, just because it's sleep comes at a premium nowadays. Okay. So Wednesday, we have our midterm exam, and so you guys have the study guide for that. The study, what is it called? The review video went up on Friday, and so you guys have that available to you guys. So hopefully that's helpful for you guys studying. Homework 6 is due today, and homework 6 is going to be covered on the exam as well. And basically right at midnight tonight, I'm going to post the solutions for homework 6 so that you'll have that available to help you study as well. Okay. All right, so today we're going to start something new. And so what we cover today is not going to be on the midterm because it's something completely different. Actually, actually almost completely different than anything that we've done in this class so far. And that's radiation. Right? So radiation is actually a very unique form of heat transfer, and that it works in a very different way than conduction and convection, which is what we've done so far. And so today we're just going to get kind of just kind of get our feet wet in radiation a little bit. We're going to define a lot of terms, define a lot of concepts. And then after the midterm until the end of the semester, then we'll really get into it. Okay. All right. So are there any questions that I can answer before we get started about the homework or the exam or anything? Okay. All right. So at any point, if there's any questions, just as always, don't be afraid to ask. And let's get rolling.
Wait, the exam is this Wednesday?
This Wednesday. Yes. Yeah. Yes. Mm-hmm. Yes, so radiation will not be on the test. Yeah, radiation will be on the final, but not on this midterm. Yeah. Okay.
That means I can take a nap.
You can. I mean, all the lectures are recorded too, so you can go back and watch them later. So, and so that's kind of the nice thing about technology that we have nowadays. Actually, I remember in college too. I mean, my lectures weren't recorded, but I would often doze off in some lectures as well. But not that you should do that, but it's it's not the worst thing in the world.
That happened to me in math class.
Okay, so let's talk about radiation. Okay, and so if you kind of think back to the very beginning of the class, we said there were kind of three different modes of heat transfer, right? And kind of the way the class is structured, we've kind of been going through each one kind of in detail. And so in the first unit for the class, all the way up until the first midterm, we went through conduction, right? And so we learned everything that has to do about conduction. Not everything, but enough detail for this class. And then last week, we just finished talking about convection, right? And so the last one that we haven't covered yet is radiation. And radiation is really like kind of the black sheep of the family, because if you compare it to conduction and convection, radiation does not require any kind of material medium. Okay, and so if we can define radiation. Radiation is a mode of heat transfer that occurs through electromagnetic waves. And so that's very different. So, so if you think about conduction and you think about convection, there's always some kind of material that was involved, right? Oh, is there a clicking sound coming through?
Yeah.
Let me see. I wonder if
Kind of like someone tapping a desk.
Let's see. I feel like this has happened
It's like
before.
some aggressive Morse code.
It's probably the sound of my my stylus tapping on my iPad. Let me see.
Is it a code to giving us a free A on the midterm?
not that I'm aware of, but it could be. Let me try rejoining on my iPad. Maybe that'll help. So right now should be no audio. Maybe my mic is a little bit too close to my iPad too. Let me bring this up a little bit.
It taps when you're not writing on the screen. So once you start once you start writing, it goes away.
Oh, interesting. That's weird because I don't hear anything on my end at all. Let me switch to oh, maybe that helps. My mic isn't even plugged in. Okay, does that help it?
Yes.
Thank you.
Okay. Yeah, I just had to plug in my mic. Sorry about that. Okay. So no material medium is required, right? And so if you think about conduction and you think about convection, you know, the way that heat is transferred in those cases was literally, you know, individual molecules sitting next to each other, and they kind of vibrate and kind of, you know, transfer heat from one molecule to the next one, right? And so when you have conduction and convection, you need some kind of matter, you need some kind of, you know, something in between. And so for conduction, you know, we mostly dealt with solids, right? And so, you know, for a solid, like a piece of metal or like a piece of plastic, right? The metal molecules and the plastic molecules are right next to each other so they can transfer heat, right? For convection, it was mostly fluids, right? And so when you had fluids moving, you know, the fluid particles, those are the things that carry heat. And then they transfer heat to the next particle, to the next one, and so on and so forth. Okay? Radiation doesn't require that at all. And so radiation occurs through electromagnetic waves, which is kind of the same thing as, you know, as light waves, okay? Right. Okay. And so if you kind of think about it, you know, if you have kind of an object like this, right? And so this object is at some temperature, right? This object right here is constantly giving off these electromagnetic waves around it. Okay. Okay. And those waves are basically radiation heat transfer. Okay. And so generally, you know, for most engineering applications, we kind of ignore radiation a lot of times. Just because, you know, if you measure the relative magnitudes of things, you know, conduction and convection are usually much higher, that you could ignore radiation. And so, but, you know, there is one big example of radiation that, you know, we see every day, or you do see it if you go outside, and that's the sun, right? And so if you think about the space that's between the Earth and the sun, there's no matter in that space, right? It's just vacuum, so that's just space. And so in order for the heat from the sun to reach the Earth, you know, it has to come here through radiation. Like there's no way that conduction and convection can occur. Okay. And another example where radiation is really important is in space applications, right? And so, you know, if you ever launch like a satellite or you launch like a rocket into space, right? Then there's going to be all of a sudden in an environment where you can't have conduction or convection heat transfer on the outside of your device, right? And so when you're designing satellites, you know, or the engineers that design satellites have to keep this in mind, that, you know, they don't put enough they don't put so much electronics on there that the whole thing overheats, because the amount of cooling that comes from the outside is going to be a lot less because of radiation. Okay, and so that's a real concern that they have to deal with. And so, you know, in kind of the short amount of time that we have left, you know, we're only going to take like a very cursory look at radiation. Because in reality, you know, radiation is you know, pretty complex. I'd say it's probably the most difficult of the three to analyze in terms of math. And so, you know, we're going to get into some of it, but, you know, a lot of it, you know, you're going to have to study, you know, further with further classes, or, you know, with further applications in order to really get a strong understanding. But, you know, at the very least, in the last few weeks of this class, you know, we'll understand what radiation is, how to do some introductory analysis of it, and you know, and to build, most importantly, you know, for me, is to build just your intuition about it, so that you can take that intuition and really take it to the next step and study more. Okay, so any questions so far on radiation? Okay. All right, so let's give some more definitions, because radiation is so different. It kind of has its own set of vocabulary to it. Right? And so let's define this E first. Okay, this capital E, and then I'm going to define this as the spectral heat flux. Okay. And so the units for spectral heat flux here are going to be actually the same units for regular heat flux, and so that's going to be watts per meter squared. Okay. And what the spectral heat flux here defines is basically the amount of radiation heat transfer that an object gives off. right, and so, it's a little bit of a change of symbols, because usually when we talk about heat flux, we usually use the term Q double prime, but for radiation, we call it E, just because the physical mechanism is very different. Okay. All right, and then the formula that we're going to have, or the way that we're going to compute this, is the product of all of these terms here. Right? And so first we have a term epsilon. Okay. Then we have a term sigma. And then we have the surface temperature raised to the 4th power. Okay. All right, so let's talk about this epsilon first. Okay. And so this epsilon is known as a quantity known as emissivity. Right. I'm going to mispronounce words all throughout this chapter. Right. So emissivity, and so the emissivity basically defines how effectively that surface emits radiation. Okay. Because, now that we're getting into radiation, we're going to talk a lot about kind of optical properties and optical stuff, right? And so, if you compare a surface like a mirror, right, or a surface like sandpaper, those two things have very different optical properties, right? So if you look in a mirror, you can see yourself, but if you look at a piece of sandpaper, you can see that it's really rough, right? And so, the way a surface is treated and the way it kind of interacts with light, that's going to start to be really important in terms of how radiation occurs, right? And so this emissivity is kind of a parameter that describes for a given surface and how that surface is usually treated, how much radiation can actually come off. Okay, and so this emissivity here it's a fraction, and so it's usually between 0 and 1. Okay. Where 1 means maximum emissivity and 0 means no emissivity. Okay, and so those are the extremes, and it's usually impossible to find something that's exactly 0 or exactly 1, and so pretty much everything will fall in between. Okay, but for the purpose of for simplicity's sake, for a lot of this unit, we're going to assume that emissivity is 1. Okay, and so emissivity of 1 means that this surface will give off the maximum amount of radiation possible. Okay. Okay. And these are special kinds of surfaces, that have emissivity of 1, and we call those black body surfaces. And so in reality, it's really, really difficult to get something with emissivity, approaching 1. And so it's more of a theoretical kind of approximation, kind of like in your physics class when you assume there's no air resistance. But for the sake of calculations, it usually makes things a lot simpler. And so, we'll be talking a lot about black body radiation, black body surfaces, and things like that. Okay, so that's the emissivity. And now let's talk about sigma here. And so this sigma is a very special constant. Okay, it's called the Stefan-Boltzmann constant. Okay. And so this constant here is kind of a you can think of it as basically just a conversion factor. And so there's only one value for sigma, and so that's all you have to do is just basically plug in for it, right? And so the value for sigma is basically 5.67 times 10 to the minus 8 watts per meter squared K. Okay. Right. And so when you plug in sigma for that, you just have to basically plug in that value. And it's basically a conversion factor between temperature and heat flux for radiation. All right. And then the last thing here is surface temperature. And so that's nothing new. And so we've been dealing with surface temperatures all along. But, because we're raising this to the 4th power, we're a little bit more restricted here. And so if you kind of think back to our, to all our previous units, when we talk about temperature, we usually put it in terms of degrees Celsius, right? But for radiation, because we have this temperature raised to the 4th power, this temperature has to be in Kelvin. Okay. And so whenever you're doing any kind of radiation computations, because we have temperature raised to a certain power, if you don't put the temperature in kelvins, you're going to end up with very, very wrong results. Okay. And so basically from here on out, we're basically going to assume that all our temperatures here are going to be in Kelvin. Okay. In the grand scheme of things, it looks like a relatively simple formula, but there's a lot of new concepts in here that I wanted to talk about. And so, that's why I kind of broke it down like this. Okay. So any questions on this so far? Okay. All right, and so that's radiation emission. Okay, and so in other words, what we define here is a formula for how much radiation an object can give off. Okay. All right, but besides emission, objects can also absorb radiation, right? And so we call that irradiation. And so this is basically the mechanism that the Earth absorbs heat from the sun, right? So the sun's giving off all this radiation, it's emitting all this stuff, but in order for the Earth to be heated by it, it has to be irradiated by it. Okay. And so the symbol that we give irradiation here is capital G. Okay. Okay. And then the formula for this is basically the following. All right, and so the amount of irradiation that's absorbed by an object is equal to alpha times G. Right? Where G absorbed here is this is the amount of heat that's actually taken in by the object. And this G on the right here, this is the total amount of radiation that hits the object. Okay. Right. And so there's a difference here. And so whenever you shine, radiation onto something, a lot of radiation waves are going to hit the object, but not every single one is going to actually be absorbed by that object, right? Because a lot of it can either be reflected, it can pass through if you have like a transparent object, it can do any number of those things. Okay, and so this alpha here, you could think of this alpha as kind of a similar type of quantity as the emissivity. And so this alpha here is called the absorptivity. Okay. And so just like emissivity, this is something that's between 0 and 1. Okay. And based on this formula right here, you can basically say that this absorptivity is the fraction of radiation that gets absorbed by a certain object. Okay. All right. So actually, let me draw a picture for you, just to kind of illustrate what this is. Okay. All right. So let's say that we have an object here, and it's potato shaped, just like all great arbitrary objects. Okay. And let's say that we put this object outside, and so it's going to start absorbing some radiation from the sun. Right. Okay. And so let's say that it's being irradiated on by the sun. Okay? And then we'll call this G, right? So the G is basically all the incoming radiation waves that come from another source. Okay? All right, and so when G hits an object, it can do one of three things. Okay, and so first thing that it can do is being absorbed, right? And so if it's absorbed by the object, it's basically taken in that radiation, and then it's that radiation is going to increase its temperature, right? And so that's how things are, or you can think of that's how things are heated by radiation. Okay? Okay. And so that's basically what we described above here. And so another thing that can happen is that the radiation can just reflect off the surface. And so if a radiation wave is reflected off an object, then it doesn't affect its internal energy at all. Okay, it just kind of bounces back and goes back to where it came from. And it's just like a mirror, right? So if a mirror, the reason you can see your reflection in a mirror is because the mirror will basically reflect all the light waves that come into it. Okay. All right, and so the last thing that radiation waves can do is that it can just pass right through the object. Right, and then we call that transmission, right? And so if a radiation wave just passes right through an object, then it just transmits. Okay? And so kind of the analogy for that is if you have kind of a clear, transparent object. So here I have my glass of water, which is empty. Okay, and so because you can see through it, we know that light waves are coming in and just passing right through the object, which allows us to kind of see objects behind it. Right? And so just like this, we can have objects that are transparent to radiation as well, where the radiation waves just kind of pass right through it. Okay. All right. And so, we have the constant here for absorption, which is alpha, but reflection and transmittance also have their own constants as well. Okay. And so reflection, the constant, is known as rho. Okay. So same symbol as density. And then for transmission, the symbol for that is tau, okay? And so if you add up alpha and you add up rho and you add up tau for any given object, they should all add up to 1. And so all of these constants here are basically just fractions that go between 0 and 1. But for any given object, radiation can only do one of these three things. And so whenever a light wave hits it, a certain percentage is going to be absorbed, a certain percentage is going to be reflected, and a certain percentage is going to be transmitted. Okay, and so if you add up all of their fractions, then they're always going to be equal to 1. Okay. Okay. So any questions on this so far? Okay. All right. And so kind of like what I mentioned at the beginning, that radiation, because of how complex it is, and with the complexity of the geometry, we're only going to stick to kind of very simple cases. Okay? And so one such simple case that we can analyze analytically is, let's say that we have a small object that's completely surrounded by a surface. Okay. And so schematically, it looks like this. So let's say, you know, our small object here is a small cylinder. All right, so let's say that we have a tiny cylinder right here, okay? And it's sitting inside a room that completely encapsulates it. Okay. Right. Let's give this cylinder a diameter. And so let's say that the diameter of the cylinder here is going to be 70 millimeters. Okay. And let's say that the surface temperature here is 200 degrees C. Okay. And then let's say that we place the cylinder in a very large empty room, and the walls of that room are at room temperature. And so let's say that T surface, let's say that this is equal to 25 degrees C. Okay? So a very hot, small object in a room that is 25 degrees C. Okay. And in particular, for this object, let's say that it has an emissivity of 0.8. Okay. All right, and so let's find the heat loss from this, let's find the radiation heat loss from this object per unit length. And so, you know, we're basically just going to be applying our equation from before, where, you know, we're going to compute the amount of heat transfer that comes off from this object, you know, and how much of that is going to be absorbed from the walls. Okay. Okay. So, any questions on this so far? Okay. All right. And so there's kind of two things that are going on here. And so, you know, one thing about radiation is that, you know, as long as an object is at some kind of temperature, or it's, you know, it's not at absolute zero, it's going to be emitting some radiation. Okay. And so if we have this object here that's at 200 degrees C, like we know that this object here is going to radiate some stuff. It's going to emit some radiation. And since the room is at a certain temperature, right? So we know the room is at 25 degrees C. This is also going to emit some temperatures, emit some radiation as well. Okay. Okay. And so if we compute the amount of spectral heat flux from both of the cylinder and the room, the net amount of heat transfer that occurs from the cylinder to the room is just going to be the difference in between these two. Okay. All right. So let me go ahead and write that out in formula form here. Okay. And so spectral heat flux from cylinder. Okay. So we have E cylinder. This is equal to epsilon times our Stefan Boltzmann constant times the surface temperature to the fourth, right? Okay. Then the spectral heat flux from the walls will be the exact same thing. We're going to assume that the walls here have the same emissivity, just because it wasn't given to you in the problem. Okay. Okay. And so the total amount of heat transfer is just going to be the difference in between these two. And so this is epsilon times sigma times Ts to the fourth minus T surface to the fourth. Okay. All right. Okay, and so if we can go ahead and plug in these numbers, and then what we get is a spectral heat flux of 1912.7 watts per meter squared. Okay. And so this is the total spectral heat flux, right? But for this problem, what we wanted to find was the heat loss per unit length, okay? Right? And so the way that we can compute that is we just take this heat flux here and multiply it by the circular area of the cylinder. Okay. All right, because we know that if we want to compute heat transfer rate from heat flux, we just have to multiply that heat flux by some area. Right. So we know that Q is equal to area times QS double prime. Right. Where QS double prime here is usually our heat flux. And for a cylinder, the surface area of a cylinder is just pi times d times the length, QS double prime, okay? And so if we want to get the heat transfer or the heat loss per unit length, we can divide both sides by L, okay? And so we see that Q divided by L is equal to pi d QS double prime. And so in this problem, we don't have QS, but we do have E, okay? And so if we replace this QS double prime by E because they have the same units, okay? Then we can compute the heat loss per unit length, okay? So we're just gonna take our answer that's boxed above and just multiply by pi times the diameter. All right, so any questions on this so far? Okay. All right, and so if we do that, okay, so let's do E per length is equal to E times pi times D, okay? And what we get is 420 watts per meter. Okay. And so that's pretty significant actually. So that's actually not bad. Okay? And so let's do a comparison really quick. So let's say that in this room, let's say that we have air that's blowing with a convection coefficient of 15. Okay. And so if we have that kind of convection situation, let's compute the amount of heat loss that we get from convection versus radiation. Okay. All right. And so we know that the heat transfer due to convection, we know is H times A times Ts minus T infinity. Okay. Where T infinity, we're just going to use the same temperature as the walls, right? And so for the area, let's plug in pi d times L, okay? And so we get Q convection over L is equal to H times pi d times Ts minus T surface, okay? And we do that, and we plug in the numbers for that, and we get a heat transfer rate per unit length as 577.27 watts per meter. Okay. And so for this case, these two are, I mean, convection obviously is higher here, but then these two are very similar. Okay. Okay. And that's kind of significant, because if you remember from the beginning of the lecture today, I said usually you can ignore radiation, but for this particular case, if you ignore radiation, you're going to be missing out on a pretty significant amount of heat transfer, right? And so in this case, it's you can almost say it's like 42%, right? And so if we ignore radiation here, we'd be missing 42% of the total amount of heat transfer. And if you can imagine, if you missed out on 42% of the heat transfer in a professional analysis, you'd be getting things really wrong, and you'd have a lot of angry managers on your ass, right? And so let's look at the situation again and see what's unique about the situation that makes it so that radiation is significant. And so, I kind of pose this question in this way because it's an important thing about radiation is to know, what are some cases where it's significant and not. Okay. All right. And so if we look at the situation again, let's focus on just the cylinder part of this equation, okay? Or this example. Sorry. In particular, we see that the cylinder here is really, really hot, right? And so, it's a little bit hard to know, just because everything in these kinds of classes are just kind of numbers on a page. But 200 degrees C is extremely hot, right? So you're talking about water evaporates at 100 degrees C, and so 200 is way more than that. So this is really, really hot. Okay. And this is kind of one of the key, the key things that makes radiation significant. Because if you look at a formula here for radiation emission, it depends on surface energy to the fourth power. Okay. Right. And so as the temperature of your object goes up, the amount of radiation that it emits goes up by a factor of 4 as well. Okay. And so usually the thing that keeps it in check for most objects is the fact that the Boltzmann constant here, Stefan Boltzmann constant, is really, really low. Right? So if you remember, its value was like 5.67 times 10 to the minus 8. That means it's 0.000000007 zeros of stuff. And so that usually makes things really small. But when your surface temperature here is really, really high, this TS term is going to overwhelm the Boltzmann constant and gives you, pretty high amounts of radiation. Okay. Right. Right. And so if we ask the question, when is radiation most relevant? The first case that we just saw in the previous example is when the absolute temperatures are really, really high. Okay. And the reason for this is because of our TS to the fourth term, right? So anytime you have something raised to the fourth power, it's going to grow very, very quickly with temperature, okay? All right. And so the second one that we've kind of talked about before is is in space applications, okay? And so in space, you know, you don't really have any conduction or convection, at least not outside your devices, right? And so you need to take radiation into account in order to, you know, properly do thermal management on your devices, okay? All right, and so another application where radiation is significant is in any kind of industrial size heating and cooling. Usually in these cases, you know, you're dealing with very, very high temperatures, right? And so whenever you deal with very, very high temperatures, you know, you have to heat, you know, a huge amount of water or a huge amount of something, you know, radiation is going to be pretty significant there, okay? And the other industry where you see radiation is significant is actually in the energy business. In particular, things like fossil fuels and solar, they have to think about radiation quite a lot. Right, and so these are kind of the general situations where you would see, you know, radiation quite a bit. Okay? And I list these things, you know, just to to let you know when you can ignore radiation and not. But when I say, you know, you should ignore radiation, it's not that it's not there, right? And so kind of like as I mentioned kind of briefly in this example, all objects will emit radiation. As long as the temperature is not absolute zero, then there's going to be some radiation that comes off. Okay. And you know, if you think about the amount of objects that are at absolute zero, you know, you can say that we can basically say that all objects emit some kind of radiation. You have to have a very, very special setup in order to get an object down to even close to absolute zero, right? And so it's not that, you know, radiation is not there. Radiation is always there. It's a matter of, you know, how high is it compared to other forms of heat transfer. Okay. And if you're dealing with, you know, somewhat mortal, you know, temperatures, you know, the ones that, you know, a lot of us come across with, you know, the answer usually is not that much, okay? With the exception, of course, of these applications. Okay. Okay. So any questions? Any questions so far on any of this?
I have a quick question. So like objects that are like, I guess, close to zero, just really far in the negative, do they basically have like zero radiation? Because like when we get to like normal temperatures, the radiation's still low.
Yeah. Yeah. So when you get down to like near absolute zero, like you're talking about like, you know, really, really cold. I mean, most people don't come across that ever in their lifetimes. And so there's very little radiation. But for objects that are like at everyday temperatures, like you sitting at your desk, or like any object that you have, like your pencil or something, it's radiating something because it's at a temperature. It's just that a lot of times we don't notice it because everything else, generally, if you're sitting in a room, generally everything in your room is about the same temperature, roughly speaking. And so everything is kind of emitting radiation, but it's also kind of absorbing that same kind of radiation from everywhere else in the room. And so kind of the net amount of radiation transfer between the objects is close to zero. And so this example that we just did was unique because we had a really hot object in a relatively cool room, and there was kind of nothing else in that room. And so in that case, we could measure some radiation because there was a big difference in between those two.
All right, thank you.
Mm-hmm. Okay, so let's talk a little. So let's start talking about how radiation travels through space, how it leaves an object, and how it can be absorbed by a certain object. Okay? And so kind of the name for this kind of section of the notes is called radiation intensity. Okay. All right, and so the first thing to kind of know about radiation is that when radiation leaves a surface, it doesn't really have a preferred direction, and so it kind of propagates equally in all directions. And so let's say that we have our surface like this. And if somehow you had like kind of special goggles or something like that, and you can view the radiation coming off, you should see that it comes out in every direction. It's basically the same thing where, like, if you took a light bulb and you put it on a pedestal and you turned it on, like you don't see a different light if you stood at it from this angle, or if you kind of rotate it and you saw it from a different angle, right? So it all looks like the same light bulb. That's because light is kind of the same thing. So light kind of propagates equally in all directions. Unless you're directing it with like a surface or something like that. But by itself, as kind of a pure light source, it propagates in every direction equally. Okay. And so for this section, now that we've kind of established that, let's talk about what happens if we put another surface on here. And so let's say that we put another surface right here. And what we're interested in is, is this object, is this other surface right here, is it going to be able to catch all the radiation coming off our initial surface? Okay. And so the answer is no, right? And so because this object, this new surface here is kind of just oriented to the bottom right here, it can really only catch the radiation that comes towards it, right? And so we kind of extend these lines here. So we can see that this line, this line is going to hit the surface, okay? This line, if I kind of bend it a little bit, reaches the surface. So that doesn't happen in reality. So the radiation is going to go straight, and you can see it hits kind of just the tip. But all these other ones, you can see that they're just going to flow right past it because they're just not in the path, right? And so, we know from the previous, pages that this object right here, the amount of radiation heat that it's emitting, right? So we computed spectral heat flux is epsilon sigma times Ts to the fourth, right? So not all of that is being absorbed, or not all of that is even hitting other objects that are near it, right? Because it's going off in so many different directions. And so this is something that, you have to kind of keep in mind when you're talking about, when you're doing radiation, that, you have to, like things like, where the object is spatially located, what angle it's at, how, whether things are blocked or not, all of these things are going to play a much, much bigger role in our heat transfer now, right? And so it almost becomes like an optics kind of problem. Okay, so any questions on this so far? Okay. All right. And so if we compare this to kind of the situation from our last example, the last example was kind of unique where we kind of avoid that situation, right? And so in the last example, what we had was kind of a small object. Okay. We had a small object in a very large room, right? And the large room kind of perfectly encapsulated it, right? And so there's basically nothing entering or leaving the room. Okay? And so because of this unique situation, everything, or all the radiation that came off the cylinder was caught by the room. Okay? And that's because the room kind of completely surrounded the object. Okay, but that doesn't happen, in general. Okay. Right. Okay, so let's start to look at kind of some more realistic situations and how we can quantify how radiation, how much of it is absorbed. Okay. All right. And so before we do that, let me just kind of comment on something that we're going to do here. Okay. And so since we know that, an object emits radiation equally in all directions around it, the kind of the most natural and the most fitting way to actually quantify this is to actually use spherical coordinates. Because the thing about a sphere, like if you think about a sphere in kind of 3D space, right? And you come and then you draw the center of that sphere, everything on the surface of that sphere is equally distant to the center, right? And so it's going to be the same thing in radiation, because in radiation, since everything is kind of being emitted, equally in all directions, kind of the key component here is kind of how far we are from the center of emission. And so kind of the most natural way to think about radiation here is in spherical coordinates, because that everything kind of in that, you can kind of think of it as a spherical shell, will have kind of the same kind of radiation intensity. Okay, so any questions on this so far? Okay. All right, and so let's take a slight dive back into geometry a little bit, and maybe cover a new concept that you might not have heard before. It's called the solid angle. And so the solid angle, you can kind of think of it as like a 3D version of kind of a regular angle. And so if you think of kind of like, I call them regular angles just because, you know, there's a, yeah, that's kind of what I think of them as, right? So if you think of like an angle in like trigonometry or something like that, right? And so you're talking about, you know, the angle between two different lines, okay? And so, you know, what the angle here kind of represents is kind of the amount of space that exists between these two lines, right? Or in other words, basically the amount of space that's kind of, we call it subtended by these two lines, right? And so you kind of think back to your geometry classes, right? We had something right here called the arc length, right? And so kind of the length of this line in between here, you know, we call this the arc length, right? And so the arc length was kind of a measure of how much, you know, how much space or the distance that this angle covers. Okay. And so if you have a higher angle, then you're going to have a higher arc length, right? And so like if you think around a circle, right? So if your arc length is maybe 300 degrees, you know, your arc length is going to be, you know, is going to go almost all the way around the circle. But if your angle is only like 45 degrees, then your arc length is going to be smaller than that, right? And so that's kind of a connection in 2D between angle and length, right? And so solid angles are kind of the same thing, but for 3D spaces, okay? And so kind of the image that I want you guys to think about is kind of like, think of either like a flashlight or a spotlight. Okay? Or in other words, you know, we're going to look at cones, right? Right. And so if you have a flashlight, right? And so schematically, you know, usually we draw flashlights like a cone, right? And so we have a flashlight here on the left-hand side. Then it would cover kind of an area like this, okay? And just like kind of a 2D angle, we can kind of define something right here called the solid angle. Okay. And this solid angle is kind of directly related to the amount of area that we have at kind of the end of the beam. Okay. Right. And so the larger your solid angle, you know, the larger your area is going to be, right? Right. And so the way that we define solid angles, we use the following formula. Okay. And so I'll call it dW for now, okay? And the way that we're going to compute it is we're going to take the area here, and then we're going to divide it by r squared. Okay. Where the area here is basically this shaded area that I have here. Okay, so dAn is going to be this the shaded area, just like that. Okay. And then r is basically the radius of this beam. Okay. So r is kind of that kind of linear distance, just like that. Okay. Okay. And so that's solid angle, and so that's going to be kind of a key component or a key concept that we're going to use as we talk more about radiation. Okay? And so are there any questions on this so far? Okay. All right. And so to kind of put it into words here, basically the solid angle. The solid angle is inversely proportional to the distance between the source and its subtended area. And so let me draw kind of two more examples here just to kind of illustrate this for you. And so let's say that we have a source just like this, right? And so the source is, is going to be our source of radiation. And so if we had a surface that was really close to it like this, right? Okay. And if we kind of draw lines from the source out to the edges of the surface, right? Then this solid angle is fairly large. But if we had another situation where we had kind of a surface of the same size, but it's really far away, okay, right? And so we had something that looks like that, okay, where R is much bigger, this solid angle right here is going to be much smaller in comparison. And so kind of the farther away your surface is, given that your surface is the same size, your surface doesn't change, you're going to have a much smaller solid angle if it's farther away. Okay. Okay. All right. So let's apply these concepts to radiation, right? And so to kind of get us started, let me draw a 2D a radiation surface down here. And we know that this surface is going to be, emitting radiation in all directions. Okay? Or in other words, we have a sphere of radiation that goes around it, right? So you can almost think of it as like the sphere of influence. Okay, so let me clean this up a little bit, just because there's going to be a lot of stuff going on. Right? And so let me draw the coordinate axes here. All right, and so we have our two perpendicular axes, okay? And since we're in spherical coordinates, we have to define two different angle types, right? All right, and so we'll call this angle with the vertical axis, we'll call that theta. And then the angle that's in kind of the horizontal plane here, kind of in the XY plane, we'll call that phi, okay? And so those are the two angles that we're working with. And so theta is the angle with respect to the vertical axis, and phi is the one that's kind of in the plane. Okay? And I always get these names mixed up, and so I don't want to confuse you guys. But usually the way I think of it is, phi down here, the one that's in the plane of x and y, I usually call that one the polar angle, and then this theta right here, which comes off the vertical axis, I usually call that the azimuthal angle, but I always get that wrong, and so don't kind of quote me on that one. But just remember that when in spherical coordinates we have these two angles that we kind of have to worry about. All right, and then around this object here we have kind of a sphere of radiation. Okay. Or for now I'm just going to draw a half sphere, right? And so let's say we have a half dome on this, and then on this sphere right here I'm going to draw a patch. And so we have just kind of another surface that's sitting on the sphere. Right? And so from this patch, we can go ahead and draw lines from the patch to the source, right? And what we're interested in is how much radiation is this patch going to receive from the original object. Right. And so to do that, we're going to use our concept of the solid angle along with the actual area of this object, and then get that done. Okay. Okay. So any questions on this so far? Okay. All right, so the first step that we're going to need to do is we need to compute the area of this patch. Okay, and so we're going to compute this area in spherical coordinates, right? Because we know that this patch is sitting on the sphere, and so we know that this patch is some radius away from the center. Okay. And we also know kind of the angles that it subtends. Okay. And so the area for that is going to be just the length times the width. Okay. And so the length of the patch is going to be r. You can basically think of this as kind of two arc lengths that are multiplied by each other. Okay. And so first one's going to be r d theta, and the other one's going to be r sine theta d phi. Okay. And so if we compute this out, then this is dA is equal to r squared sine theta d theta d phi. Okay. All right. Okay. And now that we know the area, we can compute the solid angle that this patch subtends. Right, and so we know that solid angle omega is equal to area divided by r squared. Okay, and so if we just divide this dA by r squared, then what we get is sine theta d theta d phi. Okay, and so that's our expression for the solid angle. Okay, all right. And so we have 1 minute left, and so let me give you kind of an interesting tidbit here, and let me give you the units for solid angle, right? Because we haven't mentioned that yet. And so the units for solid angle is called steradians. They're like radians, but they're solid radians, right? And so that's why we call it steradians. I actually don't know exactly where this name came from, but that's kind of what they call solid angles. And so I guess they wanted to keep it close to radians because conceptually they're similar, but kind of differentiated. They add the STE out in front. Okay. All right. So any final questions on this before we wrap up for today? Okay. All right. And so Wednesday we have our exam. And so next Monday we'll pick up this derivation where we left off. Okay. So Wednesday, I'll see you guys for the exam. And so just like the first one, if you want to come to the Zoom call, you're welcome to do that. But if you'd rather just kind of work on the exam yourself, that's fine too. Right. So the exam's going to start at 2:30 on Wednesday and it's going to end at 4 p.m. on Wednesday. Right. So I'll see you at the exam if you're going to be there. If not, then I'll see you guys next week. Right. So thank you guys.
Thank you, Professor.
Thanks, guys.
Thank you, Professor.
Thanks.
Professor, I have a quick question on on the spectral heat flux.
Yep.
When you calculated the heat loss per unit length of the cylinder, can you explain like, so like, because you had like the equation for like heat transfer written out, and then so does like, can we assume in radiation that like heat flux is just going to be the same as spectral heat flux?
Yeah. So they're the same unit, and so you know, the reason I give them different symbols is because, you know, radiation is a different different mechanism, but it's still heat all the same. And so the units for spectral heat flux is watts per meter squared. And so if you multiply you know, if you multiply spectral heat flux by area, then you get heat transfer rate, which is just units of watts. Yeah.
Okay, cool. Thank you.
Yep. Was there any more questions from you guys before we close up the call? Okay, so I'll see you guys Wednesday if you're going to come, but if not, I'll see you guys next week.